All right, we're going to talk about the supplement section here to Chapter 8. This is a section from the old textbook that we thought was valuable and needed to be included in this one. And we're going to talk about probability distributions and expected value. So the first definition here is a random variable. Now, this is just a special kind of variable that's related to probability and that represents some numerical outcome of randomness, of a random event, all right? And when you see a couple examples of these, it'll make more sense, I think, than just the definition. Classic example would be rolling a fair die, right, where the options are from the numbers 1 to 6, and so we'll look at that example in a minute here. But there are two types of random variables. There are discrete random variables where the outcomes are what we call countable. Okay, so for instance, the probability of selecting a blue car from the parking lot would be a discrete random variable because the number of cars in the parking lot can be counted. And there's clear delineations from car to car. You can't have, you know, you can't have 1/3 of a car, for example. Okay, you can't. It can't take on any value. So a continuous random variable is one that is not countable. So an example of, let's go back a second, an example of countable random variable would be, you know, cars in a parking lot. An example of a continuous random variable would be something where there's not clear segmentation of the random variable or the thing that you're analyzing. So for instance, if you want to know what's the chance of, you know, taking a group of people and selecting someone that, you know, and then looking at how much they weigh or how tall they are, there's not clear delineations, right? So you could be 180 pounds, you could be 180.278 pounds, you could be any number in between. And so that's continuous random variables. So things like weight, height, temperature, etc. Okay. Now, I don't want you to get caught up too much in this countable and thinking it has to be 1, 2, 3, 4, 5, or something like where it has to be integers. It doesn't necessarily have to be that. For instance, the amount of money that something costs would be countable because it can always be taken down to like the number of pennies, right? We could always count the number of pennies, despite the fact that something might cost $1.73 or $1.73. There's a limit to that, and it is down to the penny. But we'll try to keep the examples fairly straightforward. There are some areas where it gets a little bit tough to see the difference, but for the most part, the examples we use will be pretty straightforward. We're not doing this here. So, all right, let's talk about relative frequency tables. Now, all of relative frequency table is it just lists the frequency of different outcomes, okay? So I think it's easiest to just do one of these to see what they're like. Excuse me, we're going to talk about rolling a fair die, and we're going to build the relative frequency table, which really, relative frequency is just the frequency of the thing happening divided by the total number of outcomes. This is just probability. Okay, so relative frequency table or probability table, those mean the same thing. So the top row is all of the possible outcomes. So if you roll a fair die, the outcomes are 1 through 6. The number of ways that can happen, well, the number of ways that you can roll a 1 is just 1. You rolled 1. The number of ways that 2 can happen is just 1. How many ways can you roll 3? Just 1. All of these are 1. What's the probability that it happens? Okay, well that's going to be one possible way that can happen divided by the total number of outcomes. That'd be 1 over 6. And you can put that as a percentage or as a decimal. It doesn't really matter. It's just going to depend on what the problem calls for and what makes sense given the context. 1 divided by 6 is 0.16. If you times that by 100, that's 16.7%. So you can put 16.7% for each of these if you want. You can put 0.167. It doesn't matter. But the bottom line is that all of these will have a relative frequency of 1 out of 6, or 1/6. Okay, so rolling one die is not that interesting. If we roll two dice, and then we look at the graph, or then we look at their sums, the probability gets more interesting. So down here, I've given you all the ways that you can roll a roll two dice, right? So you can get, you've got the black die and the white die, and you could roll 1, 1, 2, 1, so on, okay? Roll 1, 2. And then if you sum them, this is all the possible outcomes, right? The lowest number would be a 2, which is 1 plus 1. The highest number would be a 12, which is 6 plus 6, and everything in between. Okay, so how many ways can you roll a 2? Well, a sum of 2. Well, there's just one way. 1, 1. That's it. Okay, so there's one way that you can roll a 2. How about 3? Well, you could roll this one or this one. So there's 2 ways that you could roll a 3. 1, 2, 3 ways that you could roll a 4. 4 ways that you can roll a 5. 5 ways that you can roll a 6. And when you roll a 7, so here's 7, right? 1, 2, 3, 4, 5, 6. There's 6 ways that you can roll a 7, but then when you go to 8, then it becomes less likely. So here's the row for 8. And so it becomes, there's 5 ways, and then 4, and then 3, then 2, then 1. Okay? So then the relative frequency, or the probability on each one, is going to be the number of ways it can happen divided by the total number of outcomes. Well, total, there's 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. So 6 times 6, so 36. So the probability here would be 1 out of 36. 2 out of 36. I'll leave myself some space so I can put the decimal in. 3 out of 36, and so on, okay? Now, for our purposes, we're going to graph this in a second. So to graph it, what we'll do is we'll take the decimals. Well, actually, we could go either way. We could use the decimals or we could use the fractions. It doesn't really matter. Whatever's easy. In fact, I'm going to leave the fractions. So this is going to be 4 out of 36, 5 out of 36, 6 out of 36, 7 out of 36. I'm sorry, 5. Sorry. 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. I'm not reducing those fractions intentionally. You'll see why in a second. Sometimes the table here, the relative frequency table, is all you need to kind of understand what the probability distribution is. But sometimes a graphical representation is nice to visualize it as well. And so if I leave these as unsimplified fractions, then I can make kind of a nice graph. You'll see what I mean here. So if I make every tick mark 1/36, then this one would be 2 out of 36, 3 out of 36, 4, 5, 6 out of 36. Okay. Along the x-axis, I'm going to put all the possible outcomes. So there's a possible outcome of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then what I'm going to do is put a bar that represents the probability of each outcome. So the probability of rolling a 2, sum that is 2, is going to be 1 out of 36. So I'll put a bar there that goes up to 1 out of 36 and shade it. 3, the probability is 2 out of 36. 4, 3 out of 36. 5, 4 out of 36, and so on. You just complete the table out here. And down the other side. For 9, 10, 11, and 12. Okay, you could shade those if you want, but you get the idea. So now we have a probability distribution that's quite easy to look at. So if I ask you a question, something like, well, what's the most likely outcome? You can just look at the highest bar. 7, rolling a sum of 7 is the most likely outcome. What's the least likely? Well, 2 or 12. So it's just a way to visualize what shows up here in the probability distribution. Kind of like a histogram is a good way to visualize data from a table. Okay, so we're going to not completely, but we're sort of shift gears now. Continuing to talk about probability, but now we're going to talk about this concept called expected value, which is a really valuable concept from probability that you can apply in different areas of your life. So imagine you're playing a game. In this game, you pay $10 to draw a marble out of a bag. There are 5 black marbles, 3 blue ones, and 2 red. The prize breakdown is below. If you draw a red, which is the least likely, you get $100. If you draw a blue, you get $20, and if you draw a black, you get 1. So you lose money if you draw a black marble. What's the expected value over the long term of the game? In other words, if you play this game over and over and over and over and over again, you play it an infinite number of times, or you play it 1,000 times, right? What is going to be your average amount that you win if you average up your wins and your losses over that amount of time? Okay, and so to figure that out, what we do is we take the probability, so the expected value, the EV, is equal to the probability of drawing a red, which is going to be 2 out of 10, and then the probability of that times the amount that you would win if you drew a red one, that's 100, plus the probability that you draw a blue, which is 3 out of 10, times how much you would win, that's 20, plus the probability that you draw a black, which is 5 out of 10, times how much you would win, which is $1.